folks. Welcome to
Vector Calculus.
in vector calculus. Today we're taking a look at one of my all-time favorite topics, which is vectors. Now, either you love them or you hate them, but I'm going to teach you vectors in a way that you're going to fall in love with them forever, okay? Vectors are an amazing thing, okay? If you know how to use them the right way, people are going to think you know magic. That's how powerful vectors are, okay? Just to give you an idea of why we need vectors, let's start with a basic example. Okay, let's get this thing out of the way. And let's see. I've got my home right here in black, and I've got school right here in red. Now, I want to get from home to school. I don't have any Waze or Google Maps. The only thing I have is you. And you're going to tell me how do I get from my home to my school. Just using common words, right? Okay, so what are you going to say? You're going to say, okay, Rifat, so what you're going to do is you're going to take a diagonal turn at a 45-degree angle, and you're going to keep on driving straight at that diagonal 45-degree angle for 3 miles, and then you'll arrive at its school. First of all, I'm terrible with directions, and second of all, that's just too much of a hassle. Why do that when all you have to do is draw a vector? All you can do is draw a vector from here to here. That's it, that's a vector, right? Why is that a vector, you ask me? Well, that's a vector because it has a length, right? It has a length. It has a length of 3 miles. You're telling me go in that direction for 3 miles. But you're also telling me one more piece of information. One more piece of information is you're telling me the direction, right? You're not telling me go 3 miles. I'm like, 3 miles which direction? 3 miles northwest, 3 miles northeast, 3 miles south, 3 miles west or east. How do I know? Well, I know because you give me a direction, right? In this case, you give me a direction of 45 degrees, right? So that tells me the direction I have to go to and how long, right? It gives me a magnitude and a direction. And hey, that's what a vector is. It's an arrow. It's an arrow. It's an arrow with a magnitude and a direction, with a size and a kind of pointer. That's it, right? Let's go over here to Geogebra, my favorite, better than decimals, by a magnitude of 10. And all we have to do to check out a vector on the xy axis is just type v is equal to 3, 4, and check it out. What is that? That's an arrow, you say. Yeah, of course it's an arrow, but it's more than that. It's a vector. And they're the same thing, right? You can see this arrow has a certain length. And of course I can change the length of the arrow. I can move it all around, and so on and so forth, right? So that's pretty amazing. Okay, so that's basically what a vector is. It's an arrow with a magnitude and a direction. All right, so now I'm going to show you some of the properties of vectors, just going through some problems. So let's go ahead and check out some problems, okay? So here's our first problem, and I'm afraid they're being blocked by that, so let's increase that on that side. And let's take a look at our first problem, shall we? Let's take a look at our first problem. Okay. Let's read the directions. In exercises 5 to 8, find the vectors u and v, whose initial and terminal points are given. Show that u and v are equivalent. Okay. So, what do we have to do? Well, let's check it out. Let's turn this into a kind of grid so you know what I'm talking about. So hopefully you see the coordinate plane right here, right now. And let me draw the x and y axes. Here's the x-axis. Here's the y-axis, and here's the x-axis. And let's plot these points. Where's 3, 2? Do you know where 3, 2 is? Where's 3, 2? 3, 2, let's say it's around here. And 5, 6. And of course we have grapes, ladies and gentlemen. Grapes are not examples of vectors, but they're a fruit. Now, if I go ahead and type in 3, 2 here, you'll see that's a point on the coordinate plane. But a point is not an arrow. So where are they getting this vector idea from if there's no arrow? Well, I'll show you where. There's actually 2 points here. There's 2 points here, right? We have 3, 2 and 5, 6. So let's plot 5, 6 here. Okay, let's plot 5, 6. And let's see where 5, 6 falls. Alright, there's 5, 6. There's 5, 6. And there's an arrow. There's an arrow that goes between these two. In fact, I can draw a vector between these two. And there's that vector. Between point A and point B. Easy as that. All right, let's look at the other one. Let's look at the other one. V, 1 comma 4. Where's 1 comma 4? Let's put it down. 1 comma 4 is right here. It's right there. And you know what? I mean, just for the sake of it, whoops. Just for the sake of it, let's put that down again. We have 1 comma 4 as our first point. And what's our second point? 3 comma 8. 3 comma 8. 3 comma 8. And huzzah! You have 2 points. But where's your arrow? Well, you gotta draw it, right? You gotta draw your arrow. So here's your arrow. Here's your vector. And what they're asking us to do in this case is to show that these two vectors are the same. They're one and the same. Well, how do you show two vectors are the same, you ask? Well, you put them over each other and you check if they're the same. Alright, let's put them over each other. And huzzah! Not only are they parallel, only are they in the same direction, they're also the same length. Right? These two vectors, the only difference between them two is that they're on different positions, right? So these two vectors are one and the same. They're the same arrow. They're just in different places, right? So see? They're the same arrow. Boom. Different. Same. And different. Same. Different. Same. Different. Hopefully you get the point. Okay. So that's how you show that two vectors are the same geometrically. But how do you show they're the same algebraically? Well, that's a different question. Let me show you how to show that two vectors are the same algebraically. Okay, so what are we going to do? We're going to go ahead and write down our first vector. What's our first vector? What's u? U is 2 points. It's the point 3 comma 2 and 5 comma 6. But there's an arrow that goes from this point, let's call it A, to this point, let's call it B. What's that arrow? Well, to find that arrow, all we need to do is just subtract the coordinates. Isn't that magical? All you need to do is 6 minus 2. What's 6 minus 2? Shout it out, ladies and gentlemen. What is 6 minus 2? It's going to be 4. It's going to be 4. Okay? And that's how we get this y coordinate. And what's my x coordinate going to be? Well, you guessed it. Now we're going to subtract 5 and 3. And what's 5 minus 3? Well, this time 5 minus 3 is just going to be pretty simple. 5 minus 3 is going to be 2. And there you go. There's the vector. Okay? 2 comma 4. What does that mean though? That means if I go back here and I put my vector is starting from 0 comma 0, which is the origin, and it goes to 2 comma 4, I'll end up with the same vector. And huzzah, ladies and gentlemen, here's the vector I end up with. That's the vector I end up with. And check it out. It's the same as these two vectors. It's the same. I put them all over one another just to show you it's all the same. Okay? So how do we show that two vectors are one and the same? We just subtract the components of their terminal and initial points. Okay? So let's go ahead and repeat that process for the other vector v. Let's try to show that it's the same. So v is made out of 2 points, once again 1 comma 4 and 3 comma 8. So if I go ahead and subtract their components, what am I gonna get? Well, check it out. What is 8 minus 4? Well, 8 minus 4 is not too hard. 8 minus 4 is just gonna be 4. Okay? And what about the x component? What's my x component gonna be? Well, my x component is just gonna be 3 minus 1. And what's 3 minus 1? That's just 2. And huzzah, ladies and gentlemen, huzzah. Do you see that 2 comma 4 and 2 comma 4 are one and the same? They're one and the same. And what does 2 comma 4 even mean? What does that mean? What does that tell you? That tells you something very special. What does it tell you? It tells you if you hop on over to the xy axis, this vector is going to be 2 units in the x direction. Okay, so I can actually show that 2 units in the x direction. So 1 and 2. Okay, and it's going to be 4 units in the y direction. So here's 1 unit, here's 2 units, here's 3 units, there's 4 units, and connect from head to tail. Okay, take the start of this vector, connect it to the end of that vector, and boom, there's the vector we've been looking for, vector 2 comma 4. Right? And if you match that up with what we get in GeoGebra, it looks exactly same, right? Okay, so that's question number 1. Not too bad, not too bad. Okay, let's move on to the next question, ladies and gentlemen. So the next question says that in the following exercise, the initial and terminal points of a vector V are given. Sketch the given directed line segment. Okay, let's do that. Let's go over here and let's sketch out what our vector should look like. And we can go ahead and disregard the question number 10. Well, we're not gonna need it for now. So let's go ahead and just take question 9, ladies and gentlemen. Just question 9. Okay. So for question 9, we're given the initial and terminal point of a vector. Okay. And what we need to do is actually show how that vector looks like on the xy axis. Well, that's not too bad. Okay, that's not too bad. Let me go ahead and draw the x-axis. Here's the y-axis. Let's make that better. So what's my initial point going to be? Well, my initial point is going to be 2, 0, right? So 2, 0 is going to be right here. Okay, I'm not being too specific, but hopefully you get the point. That's 2, 0. What about 5, 5? That's where we end up. Well, 5, 5 is going to be somewhere around here, right? 5, 5. And our vector is just going to be the arrow that connects these two dots. Boom. That's our vector, ladies and gentlemen. That right there is our vector. Okay? And you can hop over onto Geogebra. Let's check it out. Let's can I delete all of these before I draw my new vector? Let's go ahead and disable these. And let's go ahead and check out how our new vector looks like. So our new vector has initial point of 2, 0. And it has a terminal point of 5, 5. So let's go ahead and put down 5, 5 right here. Alright, so what do we see? We see the point E, that's our initial point, and point F, that's our final point. And hey, check it out. What's the vector that connects these two? What's the vector that connects point E and point F? That's the arrow. That's the vector. That's it. Okay. And as a matter of fact, we can grab that picture on and put it right in our document just for reference. Alright. Now let's go ahead and move on to the next question. What's the next question? What does question B ask of us? Alright, what does question B ask of us? Okay, well, B asks us to write the vector in component form. So let's go ahead and highlight that. Write the vector in component form. What's component form? What's component form, you might be asking. I'll tell you what component form is. Component form is actually not too bad. It's not too bad. It's just a way of writing the vector in a different notation. Okay, so let me go ahead and show you what I mean by that. First, let's go ahead and delete some of our earlier work, and then we'll be good to go. So right here, I'm going to show you what component form means. Okay, so let's say we have our vector right here. Okay, our vector has an initial point at 2, 0 and a final point at 5, 5, and the arrow connecting these two is going to be our actual vector. Okay, that's our actual vector. Now, what we want to do is write the vector in component form. What does that mean, though? That means we have to figure out how much our vector goes in this direction, the x direction, and how much our vector goes in the y direction. And turns out it's not that bad. It's not that hard. Why isn't it that hard? I'll tell you why. Our vector starts at 2, 0 and it ends at 5, 5. So what's my horizontal distance over here going to be? Well, it's simply going to be the difference in the x coordinates. 5 minus 2 is 3. What's my y component going to be? Well, it's simply going to be the difference in the y coordinates. So 5 minus 0 is going to be 5. It's going to be 5, right? Okay, so then you tell me, okay, I know the vector goes 3 in the x and 5 in the y, but how do I write component form? Well, it's easy. It's not too bad. Let's give our vector a name. Okay, I'm being a kind of rude to my vector by not giving it a name. Let's call my vector u. Okay, so if my vector is called u, I can say my vector goes 3 units in the x direction by writing 3, and then I put comma how many units it goes in the y direction, and that's going to be 5. Okay, so my vector in component form is simply going to be the following: 3, 5. Okay, all right. And that's how you write a vector in component form. Not too hard, is it? Alright, let's go ahead and move on to the next question. What is question C asking of us? Let's go ahead and check out question C. Okay, so question C says, write the vector. Oh, whoopsie daisies. Write the vector as the linear combination of the standard unit vectors I and j. I and j. What does that mean, though? I'll tell you what that means. It's actually hidden language for something super easy. Something super easy. Have you heard of building blocks? Have you heard of building blocks? Hopefully you do know what I'm talking about. Here's a Lego piece. I put another piece over it, and I make a kind of tower. I keep going. Well, guess what the building blocks of this tower is? It's going to be one of these Lego pieces, right? That's going to be the building block of the whole tower. Much the same way, the building block for a vector is going to be a unit vector. Okay? So let me show you what I mean. Let's go ahead and sketch the x and y axes here. And let me put down our initial and terminal point. Okay? Now, as you can see, our vector goes some amount in the x direction, some amount in the y direction, and it ends up being that blue diagonal line, right? Now, how much does it go in the x direction? Well, we actually found out in the last slide. We found out that it goes 3 in the x direction, 3 units in the x direction, and it goes 5 units in the y direction. 5 units in the y direction. Now, how do we write the vector? As the linear combination of the standard unit vector. Well, the standard unit vector is actually not too bad. It's not as hard as it sounds. The standard unit vector is simply going to be what? Well, let's look at the 3 we have right here. Let's look at the 3 right here. This vector, this component vector in the x direction that has a length of 3, it's going to be made of 3 tiny vectors, 3 building blocks, 3 component vectors, right? So here's 1, here's 2, here's 3. Each of them have a length of 1, 1, 1. Add up to 3. That's not too bad, ladies and gentlemen. Same thing over here. Here we have a vector. Here we have a unit 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 vector. Each of these unit vectors have a length of 1, 1, 1, 1, 1. And we have 5 of them, so that it kind of makes this yellow vector of length 5. Okay, so how do I say that as a linear combination? Well, I'm going to call these green vectors I. Okay, I'm going to call them I hat because they're in the x direction, and I'll call these unit vectors in the y direction j hat. Why not? So what I can say is my vector, remember I gave my vector a name, my vector u is going to be made up of these kind of building blocks, right? It's going to be made up of 3 I hat vectors, and it's going to be made up of 5 j hat vectors, plus 5 j hat vectors. Okay, not too hard, ladies and gentlemen, not too bad. And finally, what is our final part of this question? Let's go ahead and take a look at the final part of this question. Okay, we're asked to sketch the vector with its initial point at the origin. Okay, so we have to sketch the vector with its initial point at the origin. So, oh, whoops, hopefully you didn't see that coming. But yeah, how are we going to actually sketch the vector with its initial point at the origin? Well, it turns out it's actually easier done than said, which is something you don't hear too often, right? So let's go ahead and do it. We have our x and y axis. Let's draw the x and y axis, right? And we know our vector is something like this. It starts at 2, 0, goes to 5, 5. There's our vector. What they're asking us to do is kind of move our vector, kind of shift our vector over here. So, you know, it's the same vector, but just at a different place. Okay? So how do we do that? Well, remember, it's the same way we did it with the first question, right? Remember, our vector starts at 2, 0, 2, 0, ends at 5, 5. And so, if I shift it over if I shift it over to the origin, what am I really doing? What am I really doing? Well, what I'm doing is I'm subtracting, right? I'm subtracting what from what? Well, I'm subtracting these components, right? So if I go ahead and subtract these components, these 2x components, what's that gonna give me? 5 minus 2 is 3, right? So that's the reason my vector is gonna have an x component of 3, and it's gonna have a y component of 5 minus 0, which is 5. And so my vector ends up being 3 comma 5. Not too bad, not too bad. Okay, next question, ladies and gentlemen. Okay, we have to sketch each scalar multiple of V. Well, that's not too bad. Okay, let's go over to des. There we go. For a moment I got a vector. Here's our vector, 3 comma 5. As you can see, it's going 3 units in the x direction, 5 units in the y direction. So hopefully that makes sense. Now let's see what happens if I do the first question. Okay, so the first question asks me to take 2 times my first vector. Okay, so let's take 2 times our vector. Oh, look what happened. Look what happened, ladies and gentlemen. Look what happened. Let's actually make this adjustable. Okay, so can I say a equals 3? So look what happens. I can actually whoops, can we actually toggle this slider? Well, it seems unfortunately not, but the fact of the matter, as a matter of fact, let's call this b times u. Okay, so this will be my b value, and so unfortunately Geogebra isn't cooperating with me, but if it did cooperate with me, something very magical would happen, right? You'd see that our vector originally starts like this, but then as we take 2 of our vectors, you see it doubles, right? It kind of doubles. What if I take 3 of my vector? Hey, it triples, right? And I can keep going like that. As a matter of fact, let's go ahead and disable that grid right there, and we can see that more clearly. That's quadrupling my vector. That's quintupling my vector, right? So hopefully you get the point. So now let's go ahead and this is going to be 2 times our original vector. So that's quite amazing that the math works out so nicely, and we can put that down for a. What about minus 3 times our vector? What's that going to do to our vector? Well, let's go ahead and do it. Minus 3 times our vector. Enter, and boom, it actually pushes our vector onto kind of the other direction, right? This is our new vector. Minus 3 times our original vector kind of pushes our vector into the opposite direction. Okay, so that's quite amazing. What about a fractional amount of our vector? Let's say 7 over 2. What if we take 7 over 2 of our vector? Well, it's not too bad. What if I just go ahead and type that in, 7 over 2 of our vector, and that's gonna send my vector into this kind of arbitrary point, right? You can see the actual components of my vector, and so that's not too bad. And finally, what do I have? Finally, I have 2/3 of my original vector, right? That's gonna be d. 2/3 of my original vector is gonna look like what? Well, let me go ahead and put it right here. 2/3 of my original vector is actually gonna be smaller than my vector for once, right? That's gonna be smaller than my vector, as you can quite plainly see right here. So that's what happens when you multiply a vector by a number. It just makes it bigger or smaller, right? Remember, a vector is just an arrow. If you multiply an arrow by a number, it gets bigger or smaller. Not that hard, or at least not as complicated as it may seem at first sight. So there you go, ladies and gentlemen. And let's move on to our next question. So we have to find the terminal point of a vector given its initial point and its components. Okay. So what does that mean? This is kind of like solving a puzzle. Well, let's go ahead and put down our x and y axes. Whenever you're talking about vectors or arrows, put down your x and y axes, right? It's a service to you. It's a service to the America. So what is minus 1 comma 3? Minus 1 comma 3 is gonna be right around here, right? I'm just guessing. What about 4 comma 2? 4 comma 2, I'm guessing it's around there. Okay, but I did something wrong. Look at this. This is a vector, not a point. It's an arrow, not a point. So I don't put that. All I know is that there's a there's an ending point for my vector somewhere in this area. There's a starting ending point for my vector. I don't know where. Okay, my vector starts here. I don't know where it ends up. All I know is my vector, my arrow starts there, and it goes someplace, right? I don't know, it goes into the woods. That's what it looks like to me. So let's say my vector ends up there. Okay, well, should I make it red so it's more visible? So let's say my vector ends up there, right? All I know is that my vector is gonna go, it's gonna go 4 in this way, 4 in that direction, and 2 in the up direction. Okay, 2 in the up direction. So what does that allow me to do? Well, it's not too bad, right? If I know my starting point is 4, 2, and I know my vector goes 4 in the x direction and 2 in the y direction, all I really have to do is add those to my coordinates, right? So if it goes 4 in the x direction, you might think, hey, let me add 4 to 4. But be careful. I'm actually going to subtract 4 because I'm going 4 in the left direction, okay? So my x component, my x coordinate of my terminal point is going to be 4 minus 4. And my y coordinate is going to be what? My y coordinate is going to be 2 plus 2, right? So 2 plus 2. And so what does my terminal point end up being? It ends up being 0, 4, ladies and gentlemen. 0, 4. Alright, so let's go ahead and take a look at our next question. Find the unit vector in the direction of v and verify that it has a length of 1. Well, the fact of the matter is that the unit vector is just what it sounds like. It's a vector. It's an arrow that has a size of 1. Right, so let's go ahead and draw our x and y axes. As I said, that's what we should always try to do whenever we're dealing with arrows or vectors. They're the same thing. If you're picky about it, you might say vectors, but I warn you that vectors and arrows are really the same thing. So to make matters really simple, call them arrows. That's what I do. Okay, so we've got our vector 312. What does that mean? That means we're gonna go 3 in the x direction. Let's go 3 in the x direction. Here's 3 in the x direction, right? And if you want, I can actually put a kind of tick marks. Let's put some tick marks. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You know what? My y-axis is gonna have to be different. 2, 4, 6, 8, 10, 12. Okay, so 2, 4, 6, 8, 10, 12, and we've got our x-axis right here. Okay, so let's go ahead and see what we're talking about. I'm going 3 units in the x direction. 3 units in the x direction. So let's go 1, 2, 3. So I've just gone 3 units in the x direction. Okay. Now go 12 units in the y direction. There's 2. There's 4. There's 6. There's 8. There's 10. There's 12. There you go. That right there is going to be my vector in the y direction. And so what is my final resultant vector going to be? What's my actual vector v going to look like? Well, it's going to just connect. It's going to start at the beginning of my first vector and end at the end of my second vector. And boom. There's my vector v. Now, what's a unit vector? A unit vector is a vector, an arrow, that has the size of 1, but it's in the same direction as my original vector. Okay, so let me make matters easy. Right, so we have a vector v right here. My unit vector is going to look something like this. It's going to be a vector in the same direction as v, but it has a length of only 1. It has a length of only 1. So let's call that vector, I don't know. Let's call that unit vector u. We got to give vectors names, okay, ladies and gentlemen? Can't just keep them nameless. That's offensive and discriminatory. Okay, so to find this unit vector, what do? Well, I take the size, I take my vector v, and I divide it by its size. Right? I mean, hopefully that's not too hard, right? What's my vector v? Well, it's going to be 3, 12. 3, 12. So let's go ahead and do that. I take my vector v, I divide it by its size. So this is my vector, this is the size of my vector, and if I divide something by its size, I should get 1, right? It makes sense. If you divide something by itself, you should get 1, right? So what's my vector here? My vector here is 3, 12, right? 3, 12 on the top. How do I know that? It says it right here. And what's the size of my vector going to be? The size of my vector is going to be what? Well, just use the Pythagorean theorem. You're going 3 in this way and 12 in this way, 12 in that way. You know what? I'm actually going to color code this. So check it out. Okay, I'm going 3 in the x direction and I'm going 12 in the y direction. So what's going to end up happening? Pythagorean theorem tells me the size of my vector is going to be 3 squared plus what? Plus 12 squared, ladies and gentlemen, plus 12 squared. Okay, so let's go ahead and figure out what that is. So I'm going to have 3 comma 12 on the top, over. Okay, over the square root of 3 squared. What's 3 squared? That's 9. What's 9 plus what? Plus 12 squared, and hopefully you know what 12 squared is because I don't. 12 squared is going to be 144, right? And so what do I end up with? I end up with 3 comma 12, that's my arrow on the top, divided by square root of 153, ladies and gentlemen. And now what do I do? Well, this is not too bad. This is going to end up being what? Well, that just tells me I divide both components of my vector by that number. So instead of writing 3 comma 12, I'm going to write 3 over square root of 153 comma 12 over square root of 153 over square root of 153. Okay, let's go ahead and erase that right there. And that right there, ladies and gentlemen, is our unit vector. Okay, and how do we know? Why is it even called a unit vector, you're probably thinking? Well, because it has a size of 1. And how do we know it has a size of 1, you're asking me? Well, we know it has a size of 1, again, using the Pythagorean theorem. And as a matter of fact, we can go ahead and check it has a size of 1. Okay, let's go ahead and check that our unit vector actually has a size of 1. Okay, so go to the next slide. And right now, I'm going to actually show you why it's called a unit vector in the first place. Okay, so let's go ahead and trash all of our work right there and get that out of the way. So there's our unit vector in red in the bottom left corner, and I want to show you it has a length of 1. It has a size of 1. So how do you find the size of a vector? Well, remember the formula. You don't have to remember the formula, it's just Pythagorean theorem. Okay, so it's going to be square root of my x component. What's my x component? Okay, I think I gotta write it smaller. It's going to be my x component squared, so 3 over square root of 153 squared, and plus I'm going to add to that my y component squared. So plus, what's my y component? That's my y component. Okay, so let's go ahead and write that down. 12 over square root of 153 whole squared. Okay, and let's go ahead and check out what that's going to be. Well, on the top, for the first one, what's 3 squared? 3 squared is 9. 3 squared is 9. Okay, so 9 over square root of 153 squared is just going to be 153. And to that, what am I going to add to that? Well, I'm going to have 12 squared over here, which is 144, divided by 153 squared, which is just 153. Right? And if I add these up, what do I get? I get the square root of 153 over 153. And hey, what's that? That's the square root of 1. And hey, what's that? That's 1. That tells me my vector has a size of 1, right? And that, ladies and gentlemen, is how you show that a unit vector is actually a unit vector. Or rather, that's how you check. Okay? Alright, folks. And that's how we figure out the following properties of a vector. And that's it for this episode of Vector Calculus. And we'll